So we just saw recently how the periodic table is actually organized by the electron configuration of an element, basically that last orbital. So we saw how the first group corresponds to the last orbital having an S1, the second group has an S2. Over on this side, that last orbital will either be P1, P2, P3, and so forth. Well, these little sections that contain all elements that end with the same letter orbital are assigned block names to them. For example, these two columns that all end with an S, regardless if it's an S1 or S2, are referred to as the S block. Likewise, on the other side, all of these columns that end with the p orbital, regardless if it's a p1 through 6, all have that same p orbital shape to them, and it's referred to as the p block. And then our middle rectangle here all end with a d orbital. So as you can imagine, this entire section is referred to as the d block. And these two rows down here that are actually pulled out of the periodic table are referred to as the F block because they all end with the F orbital. So it really doesn't matter how many electrons are in that last orbital when talking about the blocks. All that really matters is what the shape of the orbital is. So the periodic table is actually divided up into different sections depending on how that electron configuration ends. Now, if we take a look at these last orbitals, we know that these exponents here refer to the number of electrons that are in that orbital. So because of the last orbitals, these electrons are the electrons on the outermost shell. These electrons are referred to as the valence electrons. The valence electrons are those electrons that actually appear on the very outside of the atom. We care a lot about the valence electrons, mainly because of the fact that these are the ones that are responsible for bonding. They're the ones that really help to determine the properties of an element. So being able to determine how many valence electrons an element has can go a long way to understanding how it's going to interact with other elements. So here we have in the S1 column, well, there's one electron here. If the last orbital is an s orbital and it's an S1, that means there's one valence electron at the end. Similarly here, the S2 has got two valence electrons. When we move over to this p side though, if we're considering something here like carbon, well, carbon ends with the p2. So we know there's two valence electrons here for carbon, but that's only in the p orbital. We need to consider that carbon, whose electron configuration ends with a 2s2 and a 2p2, that we're talking about the outermost shell, which means the outermost energy level. So carbon has an outermost energy level of 2, which means we have 2 electrons in the s orbital and 2 in the p, meaning that the elements here have got 4 valence electrons. Similarly here we have a 2s2 and a 2p3, so there are 5 valence electrons, 6 here, 7 here, and 8 here. So essentially our columns not only correspond to the letter orbital or the shape of the orbital and help form these blocks, but they also correspond to the number of valence electrons, ranging from 1 valence electron all the way down to 8. Now I skipped this D block. This D block is down here for a reason. Things get a little weird down on the D block. So let's actually take a look at the elements down on the D block. So these elements are referred to as the transition metal elements, and that is because they are able to do some pretty unique things with their valence electrons. So the d orbital is actually very, very close in energy with the s orbitals, and because of that, there's actually an exchange that can happen between the s and the d orbitals, depending which one ends up having a more stable, lower energy electron configuration. This is actually the reason why some metals are magnetic. So let's just quickly talk about what it means to be magnetic. So we've actually got different types of magnetism. The first up we have what's called diamagnetic. So diamagnetic elements are the ones that are very weak and don't really respond to magnetic fields. In fact, they repel them. And this is because all the electrons in their outer orbitals are paired up, meaning that if I have some spaces here, I'll have 2 electrons in every single line. Now, if we take a look at another type called paramagnetic, these are where the metals are actually more reactive to magnetic fields. They get attracted to them. And this is because they have an unpaired electron. So an unpaired electron is an electron that, as the name suggests, is not paired up. So most elements and most substances actually fall in this paramagnetic field range because not every element has got a paired electron. So let's take a look at oxygen. The electron configuration for oxygen, 1s2, 2s2, 2p4. Okay. If we're focusing on this outermost, that p orbital, filling this up, we can see that in the end, oxygen has 2 unpaired electrons. That makes oxygen paramagnetic. Now, it doesn't mean that oxygen is actually magnetic in the way that we know it as. It just means that when subjected to some kind of magnetic field, the oxygen will actually have a very weak response to it. But when you take away the magnetic field, those magnetic properties are gone. That's what makes something paramagnetic. That's really just a temporary thing. And then lastly, we have our permanent magnets, referred to as ferromagnetic. So they're similar in the way that they have unpaired electrons, but the difference is that enough of those atoms actually kind of get together in whatever the substance is, and they help to actually retain the magnetic properties of it. So ferromagnetic substances like iron, they can actually keep the magnetic properties when they're exposed to a magnetic field. And it's really all because of these electrons and whether they're paired up or not. So let's go and practice how to write some electron configurations without really the use of an electron diagram, orbital diagram, sorry. So here I have an image of what the periodic table looks like. Now in this image, you'll see that that F block is actually sandwiched in to the periodic table. This is essentially how it looks like. Those 2 rows are pulled out of the periodic table, mainly because the elements in this block have their own unique properties, but also the periodic table looks a lot better when you just pull it out and it's not really this whole like long conglomerate of things. So if we're taking a look at magnesium, magnesium's got 12 electrons to it. So without an orbital diagram, it's kind of hard to remember the order that the electron pairing goes in, the electron orbitals go in. Well, we just saw that the periodic table basically tells you where all the orbitals are, so it's actually possible to use the periodic table to scout out the orbital it's going to go in. So we're going to start with our 12 electrons here. So we start at the 1s orbital. Now the 1s has got 2 electrons in it. So that means that magnesium starts with a 1s2 because we have 1, 2, 1s. I need to get to 12. Next is the 2s. 2s also has 2 electrons to it. So we go 1s2, 2s2. Okay, now we've got 2 and 4 electrons. Still need to get all the way up to 12. After the 2s, it's going to follow across. We have the 2p. The 2p spans 6 electrons. So we have 2p6. Now I've got 2, 4, 10 electrons. After the 2p, we have the 3s. The 3s goes, here's my 11th electron, and here's my 12th electron. So I go to 3s2. And there you go. I just read the periodic table in terms of the electron configuration. Because again, these elements are sorted by their blocks, and we know that each column is associated with a different number of electrons in each one, and each row is associated with a different energy level. Now let's take a look at iron. For iron, rather than using the periodic table, we're going to use something called the diagonal rule. The diagonal rule can be found right here, in which all the different orbitals are listed. So the diagonal rule is really just simple. Just follow the different diagonal arrows, and they kind of tell you the order that they go in. So iron's got 26 electrons. So if I'm going to use the diagonal for iron, I'm going to start right up here, 1s. I know that all s orbitals can hold 2 electrons, so it's going to be a 1s2. After 1s, I hit the bottom of my arrow, start at the next one. Go diagonal, next up, 2s. Again, the s orbital, regardless if it's a 1, 2, or 7, can only hold 2 electrons. After the 2s, I go to the next arrow, go down, 2p. Okay, 2p. All p orbitals can hold 6 electrons. And again, if you want to check, just go right over here. 1, 2, 3, 4, 5, 6. Okay, just count the number of elements in that block, and that basically tells you how many electrons it can fit. After the 2p, we have the 3s orbital. And again, all s orbitals hold 2. So right now I'm at 2, 4, 10, 12 electrons. After 3s, we go down to 3p. Okay, so again, another 6. So now we're at 18. Okay, after 3p, it's 4s with another 2. After 4s, it's 3d. So it does get a little tricky sometimes trying to remember the order because of the fact these s and d orbitals actually start exchanging locations. As we get higher up in energy, all these different orbitals start to kind of intertwine with one another. So here I'm at 2, 4, 10, 12, 18, 20 electrons, which means that I need 6 more. D can hold 10 electrons here. So here's my electron configuration for iron. All 26 electrons are accounted for. So right now, why don't you try here with argon and chlorine? Okay, so the electron configuration for argon should look just like that. And for chlorine, just like that. Now, chlorine goes up to 35 electrons. You see all the different orbitals, that can get kind of tiring to do. So there's gotta be a shorter way to do it. And there actually is. It's about noticing something here. So if we see right over here, this electron configuration is actually right over here in chlorine. So argon and chlorine share similar parts of the electron configuration. Well, argon actually appears right here in this column known as the noble gases. Now, the noble gases are called the noble gases because of one very important reason. They have 8 valence electrons. 8 valence electrons is the key number. That is like the perfect element. So because that argon is one of these noble gases, we can actually use it. It's got a full octet. It's got a full outer shell. It has the 8 valence electrons. So we can actually use argon to substitute in here. Instead of having to rewrite 1s2, 2s2, 2p6, 3s2, 3p4, 3p6, we could just take all that info and just substitute it because we know that belongs to argon. So if we just substitute the argon symbol in here, it's essentially replacing that entire chunk, and then the chlorine notation, just whatever we have left. So this is referred to as the noble gas notation, where you're essentially just using a noble gas to substitute part of an electron configuration. And as you can see, this is probably going to be really useful whenever we're dealing with the larger elements. And the noble gas is of course chosen to be the closest one to the element without having more electrons than it. So for chlorine, even though chlorine would have been right next to krypton, krypton's got 36 electrons and its electron configuration would have surpassed that of chlorine. Argon's electron configuration fits right in here.